Okay, let's start. Hello, my name is Min-Soo Kim, and my major is physics, and I'm research in quantum entanglement in condensed matter system. So, and today's my topic is Grover's algorithm. This is my content. First, I will introduce the basic concept of Grover's algorithm. And next, I will explain geometrically. And next, I will prove mathematically. And finally, I will give you an example. First, I will explain the basic concept of Grover's algorithm. Before we start, I think many of you, okay, sorry. And first, let's think about the one problem. We have, there is unstructured data set. So, and we have to find one data. In classically, if the total number of data is n, we have to search everything n over 2 times, because there's no strategy. Just search before we find. So there's no better method in classical world. If you have a question, please raise your hand or talk me. Feel free. And okay, again, there is no better method in classical world, so we have to search before we find. However, in the quantum world, we can find in root and search. If there is 100 data set, we can find only about 10 times by using Grover's algorithm. This is today's topic. I think most of you have took quantum mechanics class, but some of you are not familiar with this concept. So I prepared the basic concept of quantum mechanics. Let's think about coin toss. In classical world, if the state of the coin is determined, the measurement value is also determined. This is mean if the coin toss, the result of coin toss is head, we can know that the result is just head 1, or tail, the result is 0. So there are only 2 possible states, 0 and 1. This is also called bit, classical bit. So superposition state is not possible in classical mechanics. However, in the quantum world, the quantum state includes the information, but we can know just the probabilities. I write the probability in red text because this is a very important concept in quantum mechanics. So therefore, the superposition state can exist like that, 0 cat plus 1 cat over square root of 2. This cannot be explained in classical mechanics. And also, in this state, we can know only the probabilities. In this state, the probability for 0 is 1 over 2, and also probability for 1 is also 1 over 2. This is a very important difference between classical and quantum world. And next, so as I mentioned, in quantum mechanics, we have to describe the system. We have to use the state. To describe state, we use cat or column vector like this. 0 cat plus 1 cat over square root of 2 is 0 cat is the column vector 1, 0, and 1 cat is the column vector 0, 1. And the square root of component of the vector is the probability of the measurement value. So in this case, the probability for 0 value and 1 value is 1 over 2. Also, there is row vector. This is notated by bra vector. Maybe you know that bra plus cat. This is a bracket notation, and bra and cat is connected. We can think inner product like this. So 0 bra inner product cat psi equal to 1 over square root of 2, or square root of 2. So I will describe of Grover's algorithm in quantum mechanics. There are total n values in data set. It's very similar with classical system. And let's think of that kind of machine. If you input x state cat and there is a black box, the function u omega, and if x is equal to omega, there is a minus sign. However, x is not equal to omega, there's no minus sign. However, we don't know the specific value of omega, so we have to find it. In classical system, we can just input x before we find. There's no algorithm. However, in quantum mechanics, we can think about that kind of thing. Initially, we don't know any information of this black box, so we can think all probability is the same. So my initial state is all values are uniformly superpositioned, like this cat. And my purpose is transform this initial vector I to omega. This is our answer. But just using this machine, we don't know about specific value of omega. And I'll explain geometrically. First, we can think there's total n space, total n values of cat. So, and in this space, we can expand omega vector and also normal omega bar vector. And we know that the initial state I can be written as like this, because the initial in the initial state, we can know that the probability for find omega is some value, and we cannot find the probability for we cannot find is also another value. And because of the normalization, we can write that sine theta and cosine theta. Initially, as I mentioned, this coefficient is the square root of the probability. So sine theta equal to 1 square root of n, 1 over square root of n. This is very small because our data set is very large, more than 10 power 10, about like that, gigabyte or megabyte. So if theta is small, sine theta is approximately theta. So we know the theta. And next, we can think about this operation. U omega equal to 2 omega cat bra minus I. I is identity matrix. It is reflection across omega bar. You know that 1 minus 2 vector is reflection about reflection, and there's minus sign. So it is not reflection across omega, reflection across omega bar, like this. And this U omega vector is same to using black box, because if the state is omega, there is no sign change. And if the state is also orthogonal to omega bar, omega, there's sign change. This is just black box. Next, we can perform the transformation. Ui equal to I minus 2 I cat I bra. This is same. It is reflection across I, like this. So, as a result, after this operation, theta transformed theta plus 2 theta. So after performing n step, the state will sine 2n plus 1 theta and cosine 2n plus 1 theta. And our purpose is making this coefficient sine 2n plus 1 theta to 1. So because theta equal to 1 over square root of n, if we perform n equal to pi over 4 square root of n step, this coefficient is very close to 1. So we can find the answer. This is Grover's algorithm. And I will give a proof of proof. The initial state is like this. The sine theta is the probability for finding our solution, and cosine theta is equal to the probability for we cannot find the state. And first, we have to operate like this. In matrix form, 1, 0, 0, minus 1. As I mentioned, this is just reflection operator. And the operation ui is 1 minus 2 I bra, I cat I bra is just with little bit calculation, you can get this form. And ui times u omega is this matrix. As I mentioned, this is just rotation matrix. So in generally, power of a matrix is kind of different, difficult problem, but for the rotation matrix power is very easy, just times n in the angle. So if you operate n times to initial state, we can get this state. It is same result as I mentioned. So I implement this algorithm in my computer. I use the Python. So there's total 100 data set. So the initial state is 1 over 100 square root of 100, and all possibility is same. A probability is same. So the probability for find proper solution is arcsine 1 over square root of 100. And if the solution, the value what I want is zeroth value, so our answer state is 1 and another value is 0. So let's multiply ui and u omega numerically. In computer, this is very easy. So, and the probability to find zeroth value is at the initial, this value. After one time, there is a small increase. And as times, the value is increasing. So at the final step, the value is almost 1. So we can get the state almost exactly. And after 7th step, sine squared 2 times 7 plus 1 theta equals 0.995. This is the same with my computer calculation result. This is the finish of my presentation, and thank you for listening. If you have a question, please feel free to ask to me.
Oh, may I ask you a question?
Sure.
Thank you for your presentation. I have a question about the geometric representation. I don't understand how UI is like reflecting matrix.
This term?
Yes. Can you explain it again?
Let's think about reflection. There is a vector, okay? And there is another vector or axis to reflect about it, okay? if you want to find the reflection vector, we have to know about the projection vector. Can you understand? Maybe you can see my mouse pointer. This is projected vector, okay? Projection vector. This is.
So you need to inner product?
Yes. This axis and this inner product of this axis and this vector is needed, okay?
Yes.
And as I mentioned, our vector is I.
Yes.
And omega, this is bra vector, and I is cat vector. If you connect them, this is just inner product. Are you understand?
Oh, okay.
So omega and I, this is inner product.
Yes.
And this is omega vector. So this term gives just projection vector, okay? And if you, in this vector I, minus this projected vector, you can get tangent vector. Sorry, not tangent, normal vector, okay? And give minus sign to normal vector, like this. You can get reflection vector, okay? This is contained in this operator. Thank you for your question.
Can I also ask one question?
Okay.
So the Grover's algorithm gives a quantum speedup in an unstructured search problem.
Yes.
So do you think if the Grover's algorithm is applied to a structured search problem, would it still give a quantum speedup?
I cannot understand your question. Can you explain one more time?
So the problem setting of the Grover's algorithm is when the data is not sorted.
Yes.
So that's why it's called an unstructured search problem.
Yes.
And if the data is in a sorted manner, would Grover's algorithm still provide us some sort of quantum speedup?
I think if the data set is sorted, I think we don't need any algorithm. We can just find. I'm understand your question properly?
If data is sorted, we can find it with log n order, so it's much faster than Grover algorithm. So yeah, we don't need any quantum algorithm.
Thank you.
Yes. So I was wondering, like, if there's like a way to modify Grover's algorithm to still give us the quantum speedup in a structured search setting, or if just barely applying Grover's algorithm to structured search might give us some sort of advantage compared to classical algorithm.
I'm sorry, but I don't know about the quantum algorithm for structured data set. I'm sorry, I don't know about this.
Okay, thank you.
Sorry.
But that's I think that's a good question to ask.
I think go ahead.
So if we have a structure data set, we usually to have an input, we need to process that input before we access the the data, right? So in order to have a structured data set, we receive data and determine where to put the data, determine the order, and then we proceed.
Oh, yes, I think, yeah, I think I understand what you mean. Yeah.
Yeah, so I think I'm not sure, but I think there is a quantum algorithm for the kind of pre-processing that gives much more, that gives some quantum advantage.
Yeah, I think that could be also one of another seminar topic, which one of us can bring up later.
Well, and for global algorithm, I think, yeah, I'm not sure that global algorithm like algorithm is applied in that kind of scenario. Okay, so does anyone have other questions?
I think there is no question.
Yeah.
I think it's very easy algorithm, I think.
Yeah, we are really very familiar with global algorithms, right? So that's why everyone here understands the context and have no
Okay,
questions.
good.
Yeah. Okay, so thank you for participation and thank you for the presentation, Mizu. And
Okay.
let's end this journal club. Thank you.
See you next time.
수고하셨습니다.
감사합니다.